All right, let's take a look at our homework from last night. It was worksheet number 9, questions 1 to 4 and 6. We're going to do a number of these questions just to make sure that we're familiar with this whole conservation of energy thing, this charged particle speeding up and slowing down thing before we have our unit assignment due on Monday and our test on Tuesday. Number 1 says an electron is accelerated from rest across a potential difference of 85 volts. What's the final speed of the electron? This electron accelerates. This electron speeds up. That's like a car doing what? An unpowered car, like a go-kart, right? Doing what? What is it? It's like it's going down a hill, right? So if we have a car going down a hill, picture this car right now going down the hill. It's at the top of the hill at rest. What kind of energy does this car have at the top of the hill as it's sitting there at rest? Maddie, what kind does it have? Good. If it was the car, it would be gravitational potential energy, right? But we know that it's not really a car, it's really an electron, so we're going to say it's electric potential energy. You can literally, like I do, write in the equation, MGH, and then erase it and put QV, or you can just kind of make that transition in your mind, in your head, and just write down QV right off the top. But I want you to picture it still as that car at the top of the hill that's not moving, that has just potential energy. Now, it accelerates across a potential difference of 85 volts. So we could say it accelerates down a hill that's of a height 85 meters. What's the final speed of the car when it reaches the bottom of the hill? What kind of energy does the car have when it reaches the bottom of the hill, Blake? Kinetic energy, good. Doesn't have any potential energy because it's at the bottom of the hill. So we're going to say that this electron also has kinetic energy when it reaches the bottom of the hill, or when it goes all the way across that potential difference. Let's sub our numbers in here as opposed to rearranging the equation first. Right now, this form of the equation isn't that hard to rearrange, but some of them get pretty ugly to rearrange if we try to rearrange them before we sub numbers in. So let's just put the numbers in. The charge of the electron is 1.6 times 10 to the minus 19. It's actually negative, as you know, but we always drop the sign of the charge. Now, technically, we have to put in the initial potential here, not the potential difference. They give me, or I give you, the potential difference here. Tell me what the initial potential would be here. What are we assuming the final potential to be? 0. The bottom of the hill has a height of 0. Okay, if the final potential is 0 and the potential difference is 85, what's the initial potential? 85, right? And that's not unique to this question. That usually ends up happening here, okay? So don't worry about that. Just say the initial potential is the same as the potential difference here, even though technically it's a different variable. That's equal to 1/2 of 9.11 times 10 to the minus 31 times the final speed squared. One of the common mistakes here would be to forget to square root the speed, the v squared, when we get to close to the final answer. But we have a nice little check on that, right? Because if we do forget to square root it, we're probably going to get something that's 10 to the 12 meters per second, which we know can't be right. So that means we got to check back and realize we forget to square root it. All right, let's say 1.6 times 10 to the minus 19 times 85. Let's multiply that by 2. 2 goes over by multiplying. Let's divide that by 9.11. And then we're going to square root it. 10 to the 13, that can't be right. So we must have forgotten to square root it. And we get 5.46 times 10 to the 6. VF, 5.46 times 10 to the 6 meters per second. Just because we get 10 to the 6 doesn't mean we're right. But if we get 10 to the 13, it means we're wrong. Does that make sense? So we get a number like this. Okay, it's reasonable. We could have forgotten a potential energy term or a kinetic energy term somewhere in there and still gotten a reasonable answer. But if we get an answer that's 10 to the 12, 10 to the 13, we know it's unreasonable, and we know that we got to try something else. Yep.
Why did you multiply by 2?
I multiplied by 2 because when I multiply these two numbers together here, this one and this one together, I get a number on the left-hand side. And then I got to take the half over to the other side. And I can do that in 2 ways. I can either divide by a half, or because the 2 is on the bottom, I can multiply by 2. It ends up being the same thing, right? Divide by a half or multiply by 2. Either way, this is a little bit easier to enter into my calculator and multiply by 2, that's all. Okay, let's take a look at number 3 next. 3 says An electron is accelerated through a potential difference of 9 volts. Once again, this electron is doing what? Speeding up or slowing down, Quinn? It's speeding up, accelerating, good. So if it's accelerating, if it's speeding up, that's like a car doing what? Going down a hill, good. So if we say that that car can be analyzed using conservation of energy, what kind of energy would that car have at the top of the first hill? Maddie, what kind of energy does it have at the top of the first hill? Okay, it has potential energy. We'd say mgh if we're talking about the car, right? Does it have kinetic energy at the top of the first hill? Okay? Pardon me? Yes, it does, because it's moving, right? So we're going to say 1 half mv squared. What kind does it have when it's gone all the way across the potential difference? In other words, all the way down the height. What kind does it have then, Dawson? Because it's moving, right? Now, what do we got to do? What do we got to change here before we actually solve this problem? Yeah, we're not really dealing with the car, right? We're dealing with this charged particle, this electron. So we're going to replace mgh with qv. And like I said, if you don't want to actually write in mgh and erase it, that's fine. Okay, I still want you to picture it as the car going down the hill. But if you want to just do that replacement in your mind, that's okay. Okay, let's sub in our numbers here. This is one that's even harder to rearrange if I don't sub my numbers in first. So definitely put your numbers into this one first. Electron is 1.6 times 10 to the minus 19 times, what's my initial potential? We're not told what the initial potential is, right, Julia? We're given the what? The change in potential, the potential difference. But look, the final potential is 0, so the initial potential is 9, same as the potential difference. M is 9.11 times 6 times 10 to the 4. That's a little slow for a charged particle. Usually it's faster than that, but it's reasonable. Just on the slower end of reasonable. All right, now follow along here on the calculator. Let's get the left-hand side. We're going to say 1.6 times 10 to the minus 19 times 9. I'm going to press equals, and I'm going to add to that inside brackets my 0.5 times 9.11 times 10 to the minus 31 times 6 times 10 to the 4. If I do the EE thing for 6 times 10 to the 4, then I can just hit squared right after it without an extra set of brackets in there. Okay, let's close that bracket off. There's my left-hand side. Now, Dawson, what am I going to do now that I've solved for my whole left-hand side? I got to take the half and the 9.11 over. How am I going to take the half over to the left side? I can divide by half, or I can multiply by 2. I don't know, habit for me to multiply by 2. It's 1 or 2 less keystrokes, I think, as well. Multiply by 2. I can divide it by 9.11 times 10 to the minus 31. Oh, 10 to the 12. Something's wrong with that. What have I forgot to do? Square root it. 1.78 times 10 to the 6 meters per second, which no guarantees it's right, but it seems like a reasonable number. No reason to go back and look for a mistake. Okay? Having said that, right, we've talked about this a number of times now. You got lots of time on your exam. I would not go and spend 5 minutes saying on this question after I've got the answer to go back and check my work. I would move on to the next question. But at the end of the exam, I would go back and try to check my work. Okay? And if you have time, like, and your mind is still there, like, try to do it again. Don't even look at your work. Just try to do it again. Yeah. No written response. Yeah. They used to do written response, and sadly, at least in my mind, they took that out. But I think it was, most students didn't really like it, but I think it was a useful thing for us to have. But we don't. Okay, not on the diploma exam. You'll have a few written response tests through the term, but separate from your regular unit tests. 4. A proton is accelerated from a speed of 5 times 10 to the 4 to 5 times 10 to the 6. What's the potential difference required to accomplish this? Proton is accelerating. The proton is, Mary, speeding up. That's like a car, Quinnen, doing what? Going down the hill, right. So if a car is going down the hill, we'd say EI is equal to EF. We'd have a conversion of potential to kinetic energy. Kind of we start with when this car is at the top of the hill. Shiva? Okay, potential energy, MGH. Is there anything else that we'd have at the top of the first hill? Yeah, we have potential and kinetic energy, right? Now, it accelerates to 5 times 10 to the 6. It's going to have kinetic energy after it's accelerated as well, right? Once it's reached the bottom of the hill. So we're going to say 1/2 mvf squared. And then we're going to replace, of course, mgh with qv. Now, I don't want to mess you up on this question. I don't want to confuse you on this question. But I want to point something out to you just so that you can hopefully have a good understanding not only of what's going on in this question, but of potential and potential difference. We want to find the potential difference required to do this. We don't know really if we're at the bottom of the hill, right? We can be a car accelerating down a hill. Halfway down the hill, maybe the car is moving at 5 times 10 to the 6 meters per second. So we don't know if the final potential is actually 0. So how do we deal with this if we don't know if the final potential is 0? Well, I'll tell you what. Let's assume that it is. We're not looking for the initial potential here. We're looking for the potential difference. So if I assume that the final potential is 0, and I get an initial potential of 10, then the potential difference is 10. If I assume that the final potential is 15, and I get an initial potential of 25, then the potential difference is 10. Which one's easier, to assume that the final is 0 or to assume that the final is 15? 0. So let's assume that. Okay, I'm going to assume that and solve for the initial potential. But remember that when I solve for the initial potential, that's not necessarily what the initial potential really is. It depends upon what the final potential is. But I'm looking for the potential difference. So it's easier to find the initial potential when the final potential is 0. Does that make sense? Okay, so let's go with this then. Let's say the charge of the proton is 1.6 times 10 to the minus 19 coulombs times VI, which I'm not really looking for, but I am looking for, plus 1/2 of the mass, which is a proton 1.67 times 10 to the minus 27 times 5 times 10 to the 4 squared equals 1/2 of 1.67 times 10 to the minus 27 times 5 times 10 to the 6 squared. Okay, I think what I want to do this time is solve for the right-hand side first. So let's say 0.5 on the right-hand side times 1.67 times 10 to the minus 27 times 5 times 10 to the 6. And because I use the EE button, I don't need to worry about the brackets when I go to put the exponent in there. Okay, there's the right-hand side. Now, watch this. I need to get this term over to the right-hand side. It's added to the VI, so let's take it over to the other side by subtracting, right? So let's say that number on the right-hand side minus brackets, because I can't just say bracket minus 1/2, so on, order of operations, right? Brackets 0.5 times 1.67 times 10 to the minus 27 times 5 times 10 to the 4. Once again, I don't need to worry about the brackets there, although I do need to close off my original brackets. 2.08 times 10 to the negative 14. Okay, that's my number on the right-hand side now. Now I'm going to do what? Divide by what? Good. gives me 1.30 times 10 to the 6, or 10 to the 5, I guess it is. Now remember, this is big V, not little v. Little v would be speed. Big V is electric potential, right? And now remember that I've solved for the initial potential, assuming the final is 0. Well, then if that's the case, then the potential difference, which is really what I'm looking for, is 1.30 times 10 to the 5. Okay? And the last question I think that we want to go over here for now is question number 6. Which says an electron begins at a speed of 5 times 10 to the 6 and is slowed down by a potential difference of 15 volts. So in other words, the electron is heading towards like a negative plate and being repelled by a negative plate and slowing down. That's like a car doing what? Harrison? Yeah, it's like a car going up the hill, not down the hill, right? So picture the car at the bottom of the hill going up now. What kind of energy, Harrison, does the car have at the bottom of the hill? Yeah, it better have kinetic, otherwise it isn't going to make it up that hill. Does it have potential at the bottom of the hill? Or? No. What kind does it have when it gets to the top of the hill? It's got potential energy, right? It's got a height as you're going up the hill. So we're going to call that QV. MGH, but we replace it with QV, right? Does it have kinetic energy? Isaac, does it have kinetic energy when the question's done? Yeah, because it says what's the final speed, right? Unless the final speed is 0, then it has kinetic energy. All right, so it's an electron. It's 9.11. VI is 5 times 10 to the 6. VF, well, the final potential we're saying is 15. Really, that's the potential difference. We're assuming the initial potential is 0. The final potential is 15. Potential difference is 15. Is 15. It's an electron again, so it's 9.11. All right, so let's get the left side this time. 0.5 times 9.11, 5 times 10 to the 6. Because I'm doing it with the EE button, then I can just hit the squared button without exponent, without brackets. There's my left side. Now I got to take this over to the left side by what? By what? By subtraction, yeah. So let's subtract and put brackets around the whole thing here. 1.6 times 10 to the minus 19 times 15. Okay. Now I got to take the 2 over, or the half over. Dawson, how do I take the half over? Times it by 2. Good. I'm going to divide it by 9.11. What'd you say there, Dawson? What'd you say there? Oh. Or 10 to the 13. And that's where we end up with 4.44 times 10 to the 6.